Good morning. Welcome back to physiology. Let's start chapter 5, and that is about metabolism and respiration of the cell. So we're going to start with the term metabolism. What does that mean? Metabolism is simply composed of two components. One is called anabolism, another one is called catabolism. Anabolism by definition means building up. If you build something, you have to spend some energy. Catabolism by definition is breaking down. Catabolism releases some energy. Anabolism is equal to endergonic reaction. Catabolism is equal to exergonic reaction. Let's take a look at this overview. We have three different types of molecules that you can break them down and create energy. One is carbohydrate, protein, and fat. Let's take a look at the carbohydrate. We have big sugars. First, you have to change it to a monomer, a single sugar, let's say like glucose. And glucose is going to go through some processes. At the end, you're going to create a bunch of ATP. You can do the same with protein. Protein is composed of a bunch of amino acids. As you can see, amino acid can be burnt and almost follow the same process to create ATP. The same is true about fat. As you can see, fat is composed of a bunch of fatty acids, and then it's going to create ATP. So we're going to start with carbohydrate, we're going to talk about protein, and then we're going to talk about fat also. The big picture here is this. To burn glucose, first we're going to burn it into pyruvate or pyruvic acid. This process of burning glucose to pyruvate or pyruvic acid happens inside the cytoplasm. This process is called glycolysis. After that, pyruvate is going to be transferred to the mitochondria, and it's going to turn to another product. It's called acetyl coenzyme A. Acetyl coenzyme A later is going to enter a Krebs cycle, a cycle that is called citric cycle, or it's called Krebs cycle. So this process starts from the glucose. First, we're going to burn glucose to the pyruvate. That process is called glycolysis. Glycolysis happens inside the cytosol or inside the cytoplasm. After that, pyruvate is going to enter to the mitochondria and is going to turn into acetyl coenzyme A. Acetyl coenzyme A in the next step is going to enter the Krebs cycle or citric acid cycle. And as a result of this cycle, you're going to create some NADH and FADH2. Now you have to turn NADH and FADH2 into ATP. And the name of the process that turns NADH and FADH2 into ATP is called electron transport system. So the point here is this. To burn glucose into ATP, we have to go through different steps. And each step is going to produce a specific product. The first step is called glycolysis. And the product of this one would be pyruvate. Let's take a look at this in more detail. Every time you burn one glucose, and you know glucose has 6 carbon, you have to first spend some energy before you create some product. In this process, I have to spend 2 ATPs. As a result, I'm going to create 4 ATPs, and then I'm going to create 2 pyruvic acid. Each pyruvic acid has 3 carbons. And then I'm going to create 2 NADH also, just like this. So if I ask you what's the end product of glycolysis, the answer is 2 net ATP, because remember we spend 2 and you create 4. So the net ATP will be 2 pyruvates, and 2 NADH. Can I use NADH directly? The answer is no. I have to bring NADH into electron transport chain to change it to ATP, and we're going to do this one later. That is your glycolysis. Let's take a look at this diagram. As you can see, you spend 2 ATP first, and then you burn it into pyruvic acid. First, you have to spend some energy to release some energy. And in this process, as you can see, you create 2 NADH as well. Now, the question is, why do we have to spend these 2 ATPs? Well, what's going to really happen is, when the glucose comes inside the cell is going to attach phosphate to it. So as a result, glucose cannot escape the cell anymore. So attaching phosphate to glucose ensures that glucose is going to stay inside the cell. Therefore, this phosphorylation will be very important. This is a detail of burning glucose into pyruvic acid. Since we are not dealing with biochemistry, which you want to take it later, I'm not going to go through detail of this one, but I want to mention a few important points. First, we mentioned so many times, you have to spend 2 ATP, then you create 4 ATPs and 2 NADH. But I also need to mention that to burn glucose to pyruvic acid, we have to first change glucose to fructose. So glucose is going to change to fructose first. And this is a fructose that is going to create really 2 pyruvic acid here. As you can see, first we're going to attach the first phosphate to the glucose, create glucose 6-phosphate. And then we're going to turn glucose into fructose and attach the second phosphate to it. Now it's called fructose 1,6 biphosphate because now it has 2-phosphate. That's one important point that I want you to know. The second important point that I want you to know is fructose 1,6 biphosphate. First, it's going to break down to 2-phosphoglyceraldehyde. This phosphoglyceraldehyde is going to go and at the end create pyruvic acid. So remember 2 things. One is glucose first is going to change to fructose, and the fructose is going to have now 2-phosphate. It's called fructose 1,6 bisphosphate, and then each one is going to create phosphoglyceraldehyde, and phosphoglyceraldehyde at the end is going to create pyruvic acid. So I think that's a couple of important things. The rest of this process you're going to learn in biochemistry. After we create this pyruvic acid or pyruvate, if there is oxygen, then pyruvate is going to come inside the mitochondria and turn into acetyl coenzyme A. However, if there is no oxygen, then pyruvate is going to turn into lactic acid. So in the presence of oxygen, remember glycolysis doesn't need oxygen, but after this point on, we need oxygen. So after you create pyruvate, if there's oxygen available, pyruvate is going to come inside the mitochondria to burn further. But if there is no oxygen available, then pyruvate is going to change to lactic acid. For example, when you're running on your treadmill, after a while you start panting. You're not bringing enough oxygen to your muscle. If there's not oxygen provided to your muscle, the muscle is burning glucose, but because of lack of oxygen, it's going to turn pyruvate to lactic acid. That's why you're going to get some spasm. Lactic acid is going to make a spasm in your muscle. So the next step is, if there is no oxygen, I'm going to change pyruvate into lactic acid. And that is shown in this diagram. Here you go. This is your pyruvic acid. It's going to change to lactic acid. The enzyme here is lactate dehydrogenase, LDH. And in this process, not only you create lactic acid, but also you burn one NADH and turn it into NAD. That means you have to spend some energy here. Again, the enzyme is lactate dehydrogenase. But why do we have to do that? Why do we need to burn NADH into NAD? That would be an important note for you to take, and that is this. Remember about end product inhibition? If you accumulate NADH inside the cell without turning it back to NAD, NADH accumulation creates end product inhibition. Is going to stop the process of glycolysis. To make sure this process doesn't stop, you have to turn NADH back to NAD. We do this one in the presence of oxygen by taking NADH into electron transport chain. When there is oxygen, we take that NADH that you made here into electron transport chain. But if there is no oxygen, that means my electron transport chain is not going to work either, then I have to burn that NADH and create NAD, and as a result, I'm going to create lactic acid. However, if oxygen is available, then pyruvic acid is going to enter to the mitochondria and join coenzyme A to create acetyl coenzyme A. Now we are right here. In the presence of oxygen, pyruvate is going to come inside the cell and turn to acetyl coenzyme A. By creation of acetyl coenzyme A, I'm going to create even more NADH. Another NADH is being built here when you turn pyruvic acid into acetyl coenzyme A. Acetyl coenzyme A later can enter citric acid cycle. Another name for citric acid cycle is tricarboxylic acid. That's why it's called TCA. Acetyl coenzyme A enters the cycle, is going to join first oxaloacetic acid, and as a result create citric acid. This is a detail of Krebs cycle. This is your acetyl coenzyme A, and it's going to come inside this cycle, join oxaloacetic to create citric acid. So the first step would be adding acetyl coenzyme A to oxaloacetic acid to create citric acid. Now, more importantly, remember to change one pyruvate, we create one acetyl coenzyme A. When you burn glucose, you created two pyruvic acid. So therefore, by burning one glucose, you also create two acetyl coenzyme A. That means you have to go through this cycle twice per glucose. Before I go further, I want you to take a look at this summary table. We said in glycolysis, I burn glucose to 2 pyruvates. And then I have to take pyruvates inside the mitochondria and turn it to acetyl coenzyme A. Since I have 2 pyruvates, I create 2 acetyl coenzyme A also. In glycolysis, I spend 2 ATP, but I create 4 ATP, and also I create 2 NADH. So that is my net result through glycolysis. In the case of turning pyruvate to acetyl coenzyme A, I didn't spend any ATP, but I created 2 NADH. And also don't forget, by turning pyruvate to acetyl coenzyme A, I also create 2 CO2. So therefore my net energy would be 2 NADH. So we learned pyruvic acid is going to change to acetyl coenzyme A. The enzyme here is called PDH, or pyruvate dehydrogenase, or it's called PDH, pyruvate dehydrogenase. In this flow chart, you can see the pyruvate can change to acetyl coenzyme A, and the enzyme is pyruvate dehydrogenase. And as a result, you create NADH. But acetyl coenzyme A not only can go through the Krebs cycle, but also can turn into cholesterol. Acetyl coenzyme A can create fatty acid. Acetyl coenzyme A can create also ketone body. So my point here is this. Although we talk about pyruvate turning to acetyl coenzyme A, and acetyl coenzyme A is going to turn to citric acid cycle, but acetyl coenzyme A can have other destinations. Acetyl coenzyme A, as a result, is a very important molecule that not only can be burnt and create ATP, but also can make other structures. Also pay attention that this arrow is only one way. In other words, you cannot turn acetyl coenzyme A back to pyruvate directly. There are other ways to create pyruvate, but it's not going to happen directly from acetyl coenzyme A. So pay attention to that. Now, clearly, if I block this enzyme, PDH, that doesn't allow pyruvate to change to acetyl coenzyme A, I'm not going to make any ATP. The only ATP I made here was 2 ATP through the glycolysis. So I'm not going to create any further ATP. That would be a problem. People who have deficiency or lack of PDH, they don't create ATP. And as a result, one of the big signs of these people is having congestive heart failure. Their heart is going to fail. Or it's called CHF. These people, they cannot pump the blood out of their heart. The heart is too weak to pump this blood out. That's why it's called congestive heart failure. For PDH to function, we need a bunch of coenzymes. One of the important ones is called thiamine. So if you're dealing with someone who's alcoholic, as you know, alcoholic people, they have very bad nutrition. They don't eat anything. They just drink alcohol. So when they come to the emergency room, let's say in coma, and you check and you see the patient is hypoglycemic because the patient, of course, didn't take any food or nutritional glucose. Before you give them glucose, you have to give them thiamine. And thiamine is an important cofactor for PDH, or pyruvate dehydrogenase. Pyruvic acid is going to turn to acetyl coenzyme A, and the acetyl coenzyme A is going to get to the citric acid cycle. When the acetyl coenzyme A gets to citric acid cycle, and it's going to join oxaloacetic to create citric acid, every time one acetyl coenzyme A goes through this cycle, the result of this cycle will be production of 3 NADH, 1 FADH2, and 1 ATP or GTP. GTP is similar to ATP. It's not the same, but it's similar. As far as the energy goes, they are very similar. So in reality, in the citric cycle, we create GTP, not ATP. However, in your book, they refer to ATP because it has the same value as far as the energy goes. So the truth of the matter here is you're going to create one GTP for every cycle. So every time you go through this cycle, what do you produce? 3 NADH, 1 FADH2, and 1 ATP. Since we have 2 acetyl coenzyme A, we have to go through this cycle twice for every glucose. So what we're going to do with this NADH and FADH2? Well, as I said, we're going to take these two and take it to electron transport chain to turn them into ATP, but we can use ATP or GTP directly. Just to remind you about our main diagram, we are right here now. So we create 3 NADH, 1 FADH2, and 1 GTP. Since we have 2 acid coenzyme A, we're going to create 6 NADH, 2 FADH2, and 2 GTP. Again, we can spend ATP or GTP directly, but to use NADH and FADH2, we have to take them to electron transport chain. And that is the one that turned this one into ATP. Electron transport chain is composed of a bunch of molecules and enzymes that you have in the crista or folding of mitochondria. The most important element of this electron transport chain would be cytochromes. The cytochromes are a molecule that contains iron. Members of electron transport chain, they're going to take electron from NADH and FADH2. This diagram shows inside the mitochondria. As you know, mitochondria has 2 membranes, outside membrane and inside membrane. There are a bunch of molecules that are sitting on inner membrane of mitochondria, and when they receive this electron from NADH or FADH2, they're going to take the electron from one member to another member to another member, but the hydrogen will be pumped inside the space between these 2 membranes. As you remember, mitochondria is composed of a bunch of folding. This folding is called crista. This is your outer membrane, and this is your inner membrane. This inner membrane has some folding, it's called crista. And in this crista, you have a bunch of molecules that they act like acceptor of electron, and they're going to pass this electron from one molecule to another molecule. This picture shows mitochondria. This is the outer membrane, and this is the inner membrane. Realize in inner membrane you have a bunch of molecules that they can accept electron. Collectively it's called electron transport chain. NADH or FADH2, they're going to bring electron to these members. This member is going to get electron, and then it's going to pump hydrogen between these 2 membranes. It's called intermembranous space. So as NADH is going to come to this mitochondria and it's going to give off the hydrogen, the electron is going to be transported from one molecule to another one, and the hydrogen will be pumped between this intermembranous space. When we get to the last member of this electron transport chain, this electron now needs to be given to somebody. Who is the biggest acceptor of the electron? We said this one before. The biggest acceptor of electron would be oxygen. So oxygen is going to get the electron, and also because of accumulation of hydrogen between these 2 membranes, there's a gradient, and this hydrogen trying to go from higher concentration to the lower concentration, and there is a protein here, it's called ATP synthase, and when the hydrogen is going to go through this ATP synthase, just like a waterfall, it's going to make this ATP synthase to become active and grab the phosphate, and it's going to give it to ADP to create ATP. This machinery works because of the accumulation of the hydrogen here. I'm sure in the biology you learn the detail of this process, but I think for our class, all you need to understand is ATP synthase allow hydrogen to go through, when the hydrogen go from higher concentration to low concentration, is going to make this ATP synthase to work, and this machine is going to give pyrophosphate into ADP to create ATP. The hydrogen, however, is going to join the oxygen to create water. So, every time you bring one NADH and give it to this first pump, at the end of this process, when the electron goes through and the hydrogen is going to come, the net production of the ATP would be 2.5 ATP. So one NADH creates 2.5 ATP. When you bring FADH2, however, the end result would be only 1.5 ATP. So for every NADH, you create 2.5 ATP. And for every FADH2, you create only 1.5 ATP. So if you think about it, we said before, glucose is going to create 2 pyruvate and it's going to create 2 NADH. Then we said 2 pyruvate create 2 acyl coenzyme A and also 2 NADH. And we said 2 acyl coenzyme A is going to go through Krebs cycle and create 6 NADH and 2 FADH2. So I'm not writing the ATP part because that's what we want to look at. So how many NADH we have? We have 2 plus 2, 4 plus 6 is 10 NADH. And each one is going to go through the electron transport chain and create 2.5 ATP. So therefore we're going to create 25 ATP altogether from NADH. We're going to create 2 FADH2, each one create 1.5 ATP. So therefore we're going to create 3 ATP right here. So that's together is going to be so far 28 ATP. You remember that in the glycolysis we already created 2 net ATP. And you remember that in the Krebs cycle we created also 2 ATP. So therefore if you add another 4 ATP here, we have 32 ATP total. So my total ATP is around 32. But many times we create only 30 ATP, and the reason for that is the efficiency of this process is not exactly what I said. This is like when you buy a car, they tell you that the car is going to give you 30 miles per every gallon of gas, but when you're driving yourself, you don't get that number because the number they give you is in the perfect scenario. The cells is not always in the perfect scenario, so many times cell does not create 32 ATP, but creates only 30 ATP. So for the sake of this discussion, we'd say the cells majority of time create 30 ATP, but sometimes 32 ATP. Because oxygen is the last acceptor of the electron, we call this process oxidative phosphorylation because after all, you have to phosphorylate ADP to create ATP, and oxygen is a main player here to accept electrons. So that's why this process is called oxidative phosphorylation. This electron transport chain is composed of a bunch of molecules like FMN or coenzyme Q, but also composed of a bunch of cytochromes. Again, I'm not going to go through this detail because this is a physiology but not major biology course, so you're going to learn about those FMN and coenzyme and cytochromes in detail in biology. But what I like to mention here is this. We have a bunch of different cytochromes. One of them that I'd like you to know is called cytochrome AA3. Cytochrome AA3 is the one that is very susceptible to cyanide or CO and is going to get blocked. Now, think about it. If you block this electron transport chain because of lack of oxygen or because you poison any of those cytochrome AA3, let's say, what is the end result? Well, if this transport of electron fails, then nothing is going to go through. That means you're not going to create any ATP. As a result, the patient is going to die. That's why cyanide intoxication is very dangerous. When you get intoxicated by cyanide or even CO, your electron transport chain is going to get stopped. As a result, you create no ATP and every cell in your body is going to go to halt, and no ATP means no life. So let me stop this discussion here, and I'm going to continue this discussion in the next section. We are not done with this chapter, but I want to take a pause here, and I'll be right back with you. Thank you.